teaching faculty member here at Perimeter Institute, and I am so happy to welcome you back to Perimeter for a special summer lecture. Perimeter Institute was created to be a place where people ask big questions about the universe. Perimeter is just over 2 decades old, but people on this land have been asking big questions about the universe for thousands of years. Looking at the night sky and understanding our place in the cosmos is a human constant throughout the ages. Perimeter is situated on the traditional territory of the Anishinaabe, Haudenosaunee, and Neutral peoples. The Institute is located on the Haldimand Tract. We are thankful to those who preceded us, and we will strive to act responsibly and collaboratively to carry forward the quest for knowledge for the betterment of all. Now, for those watching our live webcast online, we hope you'll join the conversation. We are at Perimeter on Twitter, and Perimeter scientists are online to answer your questions. If you have a question for tonight's speaker, you can ask it with the hashtag PILive. That's hashtag PILIVE. Now, this week, Perimeter is proud to be hosting the 33rd Annual Strings Conference, which brings together the extended string theory community. The Institute is truly buzzing with 200 in-person attendees and many more joining virtually from around the world. And at this time, I would like to welcome one of the organizers of the Strings Conference, Sabrina Pastursky, a faculty member here at PI, who will introduce tonight's speaker.
Hey, I'm very happy to have the honor to introduce tonight's speaker. Juan Maldacena is one of the giants of the strings community and theoretical physics more generally. His proposal of the ADS-CFT correspondence was a groundbreaking discovery that has served as a catalyst for countless research endeavors over the past 25 years, attempting to understand the deep connections between gravity and quantum field theory. Born in Argentina, Professor Maldacena received his PhD from Princeton University and is currently the Carl P. Feinberg Professor at the Institute for Advanced Study. He's a member of the American Physical Society, the American Academy of Arts and Sciences, and the World Academy of Sciences. He's received many awards throughout his distinguished career, including being one of the inaugural laureates of the prestigious Breakthrough Prize in Fundamental Physics in 2012. Tonight, he will discuss ideas that arose from the study of quantum aspects of black holes, and will also delve into how wormholes are related to quantum entanglement. Join me in welcoming Juan Maldacena to the stage.
Thank you very much. Okay, thank you very much for the very kind introduction. It's a real pleasure to be here. I've had a wonderful week during the Strings Conference, and I'll try to transmit some of the enthusiasm that we string theorists have, for our field. So I'll be talking about the meaning of spacetime, black holes, wormholes, and quantum entanglement. Okay, let me get this too. So Galileo said, well, I had my title slide. Let's see. Okay, this is not plugged in. Okay, there it is. Okay, that's the title slide. So Galileo said that the book of nature is written in the language of mathematics and geometry. So let's talk a bit about geometry. Don't worry, I will not talk to you about mathematics. So we'll talk about geometry. Let's start with Euclidean geometry. So it's based on very simple concepts such as points, lines, mainly straight lines, circles, etc. And out of these concepts, we can use it to do many things. For example, we could use it to describe images. In fact, many software programs use this type of geometrical concepts to store the images and so on. This is just an example. Now, geometry arose from technological necessities of the time, like measuring fields, levying taxes, etc. The Greeks formalized and abstracted the rules of geometry, and they summarized them starting from some axioms. And they had a list of axioms, so Euclid had a list of axioms, and one of them was, for example, just to give you an example, that if you give 2 points, any 2 distinct points, then there is a unique line, that unique straight line passing through them. Okay? That's, I guess, something we all think it's obvious. That's a starting point, and if you assume this, then you can prove many other things. Now, this process of formalizing geometry, these geometrical constructions, has continued to this day. And in fact, now we can imagine curved geometries and higher dimensional geometries and so on. And we have similar principles to describe all of these cases. Now, geometry is a very basic notion. It is possible even to find it in unexpected places. And so I'm going to give you an example of how we can find it even in children's games. So there is this game called Spotted that has many different cards with different images. And when you play, you have to match an image that is in your card to the image that's been played, to the image in a card that's been played. And by the way, I'm not getting any ad money. So, for example, these are the cards, and for example, you have these two different cards, and then you can find the image that is in common between these two cards. Can you find it? Yeah, there it is. So, for example, between these two other cards, there is also an image in common. Can you find it? Okay, good, good. You're getting good. Okay, so we are not going to continue. So what we see is that given any two cards, there is a unique image in common. Now, there is a kind of geometry behind this game. So I just said that given any two different cards, there is a unique image in common. And this sounds similar to that postulate of geometry if we replace the word cards by points and image by lines. So we can, from this little game and this little system of cards, we can abstract this notion of geometry. And in fact, so we define replacing the names in this way. There is a geometry behind this game. In fact, something called finite geometry, which is something that was developed in the 17th and 18th centuries. There is also higher dimensional geometry behind language models such as ChatGPT and, well, a lot of software programs. For example, in that case, words are represented as points in some higher dimensional space. That's another example. Now, these concepts of geometry were used to measure the geometry of our real world, the Earth. So Eratosthenes developed this simple observation where he noticed that if you have a vertical stick at some time of the year, it has no shadow, but if you move some distance away, it will have some shadow. And then by measuring this angle and this distance, he could estimate the size of the Earth. In particular, he showed that the surface of the Earth is not flat, but it's a curved space, it's curved geometry. So this shows, for example, that Euclidean geometry was wrong for measuring fields. So you have to use a different geometry, the geometry of a sphere. Of course, it's that little mistake that you make is small for small fields. It only gets big if you were to measure fields which are the size of a continent. Okay. So the notion of Euclidean geometry continues to be good for relatively small objects, such as small fields. But it's one of the first examples where we go from this flat geometry to the curved geometry. Now, still at the time and till the beginning of the 20th century, it was believed that Euclidean geometry was a good description for describing the three-dimensional geometry of, let's say, outer space, or the space in which the Earth sits. Okay, now let's make a small break from geometry and go back to physics. There is an important physics principle from the beginning of the 20th century, which is the principle of special relativity. The principle of relativity itself is older. It goes back to the days of Galileo, and it says that observers moving with constant relative velocity observe the same laws of physics. So if you are in a moving cart and someone is in a stationary cart, they both make the same observations. Now, special relativity has one extra postulate, which says that the speed of light is the maximal speed of propagation of signals, and also it's the same for all observers. So all observers measure the same speed of light. So this is an additional law of physics and in accordance to the first postulate, it's the same for all of them. So this is a little graph, and here we have the red observer is stationary, sees the light traveling at a certain speed, and then we have the moving observer, and your intuition would say that what speed would he measure? Would he measure the lower speed or the same speed? Lower, exactly. That's what your intuition would say. But the idea in physics, in reality, this person actually sees exactly the same speed. And the only way this can work is if time flows differently for the two observers. So the two observers have a different notion of time, and that's a consequence of this principle of special relativity. So what this implies is that we can join space and time into a new kind of geometry. So we can play a game somewhat similar to the game we were playing, this children's game we were discussing. We were going to discuss a new kind of geometry where we are going to define a point in a slightly different way. So we're going to define a point as an event, something that happens at some place in time. So for example, a point would be the beginning of the lecture that happened here in this room. Okay? And we can draw that, for example, if space was just one-dimensional, we have this is the direction of space, and for us sitting still, this would be the direction of time. And then after a while, at the end of the lecture, we'll have another event, which will be the end of the lecture. That's this other point. And so those are 2 points. Now, lines will be trajectories of particles or observers. So for example, if you are sitting in your chair, you are not moving anywhere, so you are sitting, hopefully, during the whole lecture. Hopefully, you won't leave during the middle of the lecture. Then we can have a particle, let's say a neutrino, that came from the sun and went through us and crossed us at the beginning of the lecture. By the end of the lecture, it will be that neutrino will be very far away. Okay? We can have one that is traveling a little faster. And finally, we can have a light ray which travels as fast as possible, and that's the maximal propagation. So any straight line of an observer moving with constant velocity will be within that. Well, we'll have it to travel within this range if it's traveling, let's say, to the right. Now, so the light ray goes at the maximal velocity. Now, something interesting is that this, so if we are the static observer, we divide space and time according to this, let's say, axis. So this is space and this is time. If we are a moving observer, like let's say this one, we would call our time direction. So we are just sitting here. For us, as we move forwards in time and not moving in space, that would correspond to, let's say, this axis. That's this axis. An axis of equal time would correspond to, actually it turns out to correspond to a line like this. So what they call space and time, each of these observers, how they divide space and time, depends on the velocity they are moving at, but they are all seeing the same, let's say, combined space-time. So the conclusion is that out of space and time, we can make a geometry in the way that we just mentioned, and that's the geometry used to describe physics in accordance to the principles of relativity. Now, we'll make a small apparent detour from geometry, and we'll talk about the force of gravity. So the force of gravity, you probably remember from your high school days. So you have two bodies, let's say a big mass and a little body, small mass. And the force of gravity says that the acceleration that this mass feels is, first of all, independent of this mass and proportional to the other mass and the distance and the Newton constant. Now, there are two things I want to draw your attention to, is that the acceleration of this mass, so how this mass will move, is actually independent of its mass. The second aspect is that the force is instantaneous, so that it only depends on where these masses are. So for example, if I were to move this mass, if I suddenly move this mass, immediately this other mass will feel the force changing. Now this is bad for relativity, so the Newton's law has to be changed so as to make it consistent with the principle that no information can travel faster than the speed of light. However, this first fact will be something that will be retained. In fact, that observation is something that Einstein called his happiest thought. And this is the idea that if you are falling freely in a gravitational field, your weight disappears. So in other words, the main effect of gravity disappears. So for example, if you are sitting in an elevator, you are standing in an elevator on top of, let's say, a scale, you will see your weight. But then if the wires break and you are falling freely, then you're falling at the same rate as the elevator and the scale and so on, and your scale will show 0 weight. Okay? Weight has disappeared. Now, I don't recommend doing this experiment in an elevator, but I'm told that it's very, very fun to do this experiment in outer space. I haven't done it myself. But the astronaut and the spaceship are both falling in the gravitational field of the Earth, orbiting the Earth, and both moving in exactly the same way, and they feel the astronauts feel they are floating. Okay, so based on that observation, Einstein developed the idea of general relativity, and general relativity is Einstein's theory of gravity, and the basic concept, the basic idea is that the geometry of space-time is not flat but is curved. And the idea is that if you are a particle moving freely, falling freely, that particle will move along that space-time along the shortest trajectory. So the analog of a straight line is the, in some sense, shortest trajectory. And then he had the idea that this curvature is produced by the presence of matter. So he had an equation which basically says that the curvature of space-time is proportional to the amount of matter that you have. So our conclusion is that space-time is really described by this curved geometry. And again, as we said before, points are events, and straight lines are the trajectories of observers falling freely. And for our everyday experience, of course, that space-time is pretty close to flat space. Now, in some cases, you can really see very clearly the curvature of space-time. So this is an example where we are here at the Earth, and we are looking back at the universe, and this is called gravitational lensing. So here we have a cluster of galaxies, which is just a big mass that curves the space-time geometry, and then the light ray that comes from a galaxy that is even further away will follow the lines of, let's say, straight lines. And here we see that we have two straight lines that initially are moving apart from each other, and then they meet again. So that's something that could not happen in flat space, where two lines that are initially moving away from each other would continue moving away from each other. But here they come back to the Earth, and in the Earth we see two images of the same galaxy. So a very clear demonstration of the curvature of space-time. And it is somewhat, in some sense, similar in spirit to how Eratosthenes showed that the curvature of the Earth that the Earth was not flat by looking at the trajectories or the properties of light rays. Now, this theory makes one interesting prediction, which is the existence of gravity waves, which was detected a few years ago, and where researchers here at the Perimeter played and made interesting contributions to this discovery. Now, in addition, there were two very surprising predictions, black holes and the expansion of the universe. And I call them very surprising because Einstein himself didn't quite believe these predictions. So when people started talking about these things, he was so surprised. He said, "No, this can't be. You must be doing something wrong." In fact, there is this famous phrase, "Your math is great, but your physics is dismal." This is what Einstein told Lemaitre. And I like this phrase very much because that's sometimes what other physicists tell us string theorists. Now, we now have great observational evidence for both. We have this picture of a close-up of the black hole at the center of the Milky Way that I'm sure you've seen. Black hole is roughly there. And this is taken by the Event Horizon Telescope. And again, researchers who work here at the Institute participate in this wonderful experiment. And we also have a lot of evidence of the expanding universe. I'm sure you've seen this picture. I won't explain it in detail. Only just to mention that we have a lot of evidence from the cosmic microwave background, of course, the whole history of the formation of galaxies and so on. And now we'll turn to a new topic. We'll make a slight change, and then we'll try to go back to gravity. And the new topic is the other revolution of the early 20th century, which was the development of quantum mechanics. So classical physics was changed in two ways. One was the development of special relativity, the relativity of time, and the discovery of spacetime. And then the idea of the curved spacetime or general relativity. And now we're going to say a few words about quantum mechanics. I'm sure you've heard something about quantum mechanics before. And quantum mechanics is a new type of description of physical systems that the main point is that it is intrinsically probabilistic. So things are not completely determined, but there is a certain probabilistic element. And then there are a few other properties of quantum mechanics, such as the uncertainty principle. There are some things you cannot know at the same time, like the position and momentum of a particle. And also there are other features, such as the so-called sum over path, that sometimes if a particle can go either through one slit or another slit, there is a sense in which the particle goes through both slits, and then there is some interference effect similar to a wave for the probability of finding the particle at this point. Okay, but what's important, something that's important for us is that quantum mechanics explains many things. It explains chemistry, it explains atoms, it explains matter, etc. Now, it's a pretty weird explanation of matter where atoms are mostly empty space. So the size of the nucleus is much, much smaller than the size of the atom. And in fact, it required a lot of work to explain simple, obvious things. So there are some things that we take for granted, but in this quantum mechanical description of atoms and matter are actually very interesting. In fact, the physical appearance of most substances are what we call emergent properties. So if we say, well, why is the screen white? And why is, it's because of how it reflects the light, and perhaps we have my computer is shiny, so why is the computer shiny? Well, it has to do with particular properties of the arrangements of many atoms. And so they arise from a large number of quantum particles and their interactions, so many of these properties. So for example, a mountain can appear very solid. Also, the water can appear very solid to the insect. The water would not appear solid to us. And in fact, the mountain also would not appear solid if you were a neutrino or a dark matter particle that can just pass through the whole mountain without interacting with anything. So in both cases, the mountain or the water consists mostly of empty space, and these solid properties that we take for granted come out of the interactions between these different particles. Now, so that's an important concept, this idea of emergence. And now we'll introduce yet another concept. So in the history of the 20th century, people put together the idea of quantum mechanics with the idea of special relativity, so the idea that signals can propagate at most with the speed of light, and this led to the modern description of particle physics, which is called quantum field theory. You could call it relativistic quantum mechanics. It describes the behavior of elementary particles, the interactions between elementary particles. So in this description, each light, for example, is described in terms of the quantum of light, which is a kind of particle, and it can be exchanged between charged particles, and that leads to the attraction between the charged particles. And in the same way that we can describe pictures using geometrical concepts, we can describe the evolution of particles in our universe by a set of lines that there are geometrical concepts which exist in space-time. So now this picture here is in space-time, and there are particles and their interactions. And this type of diagrams represent, so that they can represent the propagation of these particles, and there is a way to calculate the probabilities for each of these diagrams. So quantum mechanics is probabilistic. And so there are formulas behind these pictures, which we can use to describe particle collisions, and it agrees very well with what we see in particle collisions. Okay, and in this way we can describe all the matter we see at the very fundamental level. We describe with this type of pictures. So particles moving in the space-time geometry. Now, there is an important question, which is whether we can include gravity. Can we finish the developments of the 20th century and put together general relativity with quantum mechanics? So we know nature is just one. It's not divided into gravity and electromagnetism or matter. This is just a division in our mind. Nature is just one. And we should have a way to describe quantum gravity, but we should have a consistent way of discussing general relativity together with quantum mechanics. Now, there are two approaches to this problem. And one is an approximate approach, which is similar to the quantum field theory approach. And it's an approach, as I'll review, works well for some problems, but not for others. And then there is a more precise approach, and it's what we would call a full quantum theory of gravity. And I will start with the approximate approach. So in the approximate approach, the idea is very similar to the idea that one had for ordinary particle physics. We will just now have all these particles moving, instead of them moving in a flat geometry, they are moving in a curved space-time geometry. And again, you can create particles, and you have to add one particle, which is the graviton, pick the quantum of gravity. And in this way, you can describe various things. And when the radius of the curvature of the universe is very much larger than the so-called Planck distance, this works very well. And in particular, so let me just say what the Planck distance is. So Planck distance is a combination of the various fundamental constants of nature, G Newton, H bar, and C. So these are basic constants, and out of them we can make a quantity which has dimensions of length. And Planck made this combination when he discovered the Planck constant. And he said this distance must play an important role in physics. It's a very, very tiny distance, so it's not a distance we can see with a microscope. In fact, our best microscopes today can explore a distance of order 10 to the minus 18 meters, so a distance much, much bigger than 10 to the minus 35 meters. Just to give you an idea of the size of the Planck scale, let's imagine that we grow to the size of the galaxy. Okay? Now we are the size of the galaxy. The minimal size we can see today with our accelerators would be our size. Okay? So it's a big difference. The Planck scale would be the minimal size we can measure today with accelerators, so another factor of 10 to the 18. Anyway, this is a very tiny distance, but it was recognized as a basic length scale of general relativity. And it's basically the length scale at which the quantum effects of gravity become very important. So if you were to look at space-time at this very tiny distance, space-time would be highly fluctuating and so on. Would be very probabilistic. Space-time at long distances is very, very sharp and clearly defined, very classical. So this approximation, this simple approximation to quantum gravity is good enough for most circumstances of daily life. In fact, it's also good enough for almost all places in our universe. Now, there is a situation where there is a complete failure of this approximate description, and this happens at two places. So the most interesting one where it happens is at the beginning of the Big Bang. So at this very first instance, we think the curvature of space-time became very large. And the word singularity means, if you don't know what it means, you get the right meaning, because we don't know what happens there. So, you know. Just means we don't have any idea of what happens there, and according at least to this theory. And the other case is singularity. There are similar singularities in the interior of black holes, as I'll explain in a little while in more detail. So these are places where the approximate theory fails. So it fails in these extreme circumstances. And this circumstance here is, of course, very important for us because that we would like to understand what happens there. We would like to understand the beginning of the universe. Okay. So that's the main motivation to study quantum gravity, is to understand what happened at the beginning. So for that, we need a full theory of quantum gravity, the full theory. But before we start talking about the full theory, let me continue. We'll come back to the full theory later, but let me discuss some important successes of the approximate approach. So now we go back, take a step back again, and we'll discuss in more detail some important successes of that approximate approach. So the first one is that it leads to a big surprise for black holes. And this is the fact discovered by Hawking that made Hawking very famous. The idea that black holes, the laws of quantum mechanics in the context of black holes implies that black holes can emit thermal radiation. They emit some radiation. And this radiation is such that the temperature of the radiation increases as the black hole size decreases. So if you have a smaller black hole, it will look hotter. It would be like hot, let's say it could become red. And if it shrinks enough, it could even become white. So it could be so hot that it could have the temperature of the sun, and it would look white to our eyes. So it would be a white black hole. It looks like a contradiction in terms, right? Black holes were supposed to be black, but now they're black, they're white. So big surprise. Now this effect is almost irrelevant for astrophysical black holes. With astrophysical black holes, well, they're completely irrelevant for astrophysical black holes because astrophysical black holes are very massive. They have very low temperature, so low that it's even lower than the temperature of the cosmic microwave background, so you have no hope of seeing this tiny temperature for astrophysical black holes. If you had smaller black holes, the effect can become bigger. For example, a black hole of the mass of a continent would have the size of the bacterium, the size of the wavelength of typical wavelength of white light, and then that black hole would really look white. Okay? Now, this type of black holes are not readily made in our universe, but in theory, this is what you would find. Now, let me just explain why that effect happens. So I'll explain it with some kind of cartoons. And the point is, the basic point is that the quantum vacuum is a somewhat complicated state. So the quantum vacuum is such that if you looked at the small region of the vacuum, what you measure is quite unpredictable. So you have so the measurements at that point could change from measurement to measurement, and there is a kind of lack of information that you have if you only look at the little portion of the vacuum. And this is a computer simulation for a particular quantum field theory. The whole vacuum is simpler. So if you look at the whole vacuum, then you see, for example, that you have no particles. If you look at the small portion of the vacuum and you look there, it might be that you see something like a particle. But if you look at the whole vacuum, you don't. And the reason is essentially that you have some ignorance in some parts, but that ignorance is correlated with some other ignorance you have in the other part. If you look only at the other part, but if you look at the whole, you have a complete picture which produces a more predictable and precise state. Now, this might have looked a little abstract, so since it was a bit abstract, let me just describe it with an analogy, because it's an important point for the rest of the lecture. And imagine that somebody tells you a portion of a sentence. So let's say Mary stepped out of her, and then you can decide how to complete the sentence. Any volunteer to complete the sentence? Want to complete the sentence? Bloomers. What? Good, so that's one possibility. Okay, so you can complete, and we'll all perhaps come with different ways of completing this sentence. And so we have a certain lack of information of what the sentence is. There are many possibilities for what lies outside the sentence. So we cannot say what the sentence means. It doesn't have a definite meaning, definite, clear, crisp meaning. Now, we know it involves Mary, but we don't know the full meaning. It could end in different ways. But if someone told you the full sentence, let's say Mary stepped out of her comfort zone by explaining quantum physics to a group of investors, then you have the full meaning. Now it's clear what the whole thing is. So if you have the whole picture, clear meaning. If you have only a small picture, so that's similar to looking at the portion of the vacuum versus the full vacuum. Okay, so in that case, you get a well-formed sentence. You have a portion, we lack some information. And in fact, there is a way to quantify the information we lack. So in the case of the sentence, we could imagine listing all the possible ways to complete it. Some will be very improbable, some will be more probable. And we can quantify, there is a well-defined way to quantify the entropy or the lack of information that we have. Using so-called information theory, we can assign a number to, roughly speaking, counting the number of different ways in which it can end. So I said the vacuum is then in this analogy like a well-formed sentence. So now let's return back to black holes. And so this is a picture of the space-time geometry around the black hole. Remember, roughly time is roughly like this, and space is roughly like horizontally. Exactly what you call space and time depend on how you are moving, but roughly speaking is that. So each point here is an event that happens in a space-time. Light rays are moving at 45 degrees. And this region here is the outside of the black hole. And if you are here is the region that looks like flat space far away. So if you have a light ray that is coming out, it will go out like this. So here, this direction, you can think of it as the direction that comes out of the black hole. So, and then there is, if you are at some event here and you shoot a light ray going outwards, that light ray will go up, but then eventually it will collapse into a singularity. So we have here a singularity in the future. So this is a bit like a big crunch. So the interior of a black hole looks like a big crunch geometry where the universe collapses at some finite time. So if you're traveling here as an observer, you find that your universe collapses and you die when you get to the singularity. So I'm sorry, that's what general relativity says. Okay, so and not only do you die, but there is no way to escape from this according to general relativity. What was the question? Yeah, that's right. You can't escape because that would require you to travel faster than the speed of light. So the speed of light moves here at 45 degrees. If you wanted to escape, you would have indeed to travel faster than the speed of light. Absolutely correct. Okay, so that's the space-time geometry. And there is a particular light ray, which is the one that divides the region from which you can escape from the region where you, so the region where you can escape, which is this one outside, from the region where you cannot escape. And we call that the horizon. So this is some light ray. And so if you are an outside observer, you can see only a portion of the geometry, so the portion that is outside, because the points here, the events that are inside, can never send you a signal. So you ignore what happened here in the interior. You can only measure what happens here in the exterior. So we had the vacuum of space-time, the whole space-time vacuum, and it's split by the horizon into two pieces, the piece outside and some piece inside. And so we have a phenomenon similar to what we had with the sentence, in the sentence analogy, where we get only a portion. And because we get this portion, it leads to some ignorance, some randomness. And in physics, this ignorance or randomness translates into temperature. So whenever we have something at finite temperature, we have this feature. And the quantification of this lack of information is sometimes called entropy or disorder, is what the lack of information of what's inside. Now, from the black hole, we can calculate this entropy or amount of disorder using the laws of thermodynamics. So Hawking gave us the formula for the temperature of the black hole as a function of its mass or its energy. And then we use the laws of thermodynamics, and we can get an entropy. And it turns out that the entropy has a very simple formula, which is just the area of this horizon. So this is like a sphere. It's the trajectory of those light rays. And it's the area, so the area has some dimensions of length, and divided by that Planck length, the same quantity that Planck had originally thought that it might play an important role, here indeed plays an important role and appears in this formula. Of course, since this distance is very tiny, if you have a macroscopic area, this is a huge, huge, huge entropy. In fact, if you were to calculate the entropy of the universe, most of the entropy of the universe comes from the entropy of the big black holes at the center of galaxies. That is more important than any other entropy. And then the second law of thermodynamics would imply that the area should increase. And indeed, the laws of general relativity say that the area always increases. So Hawking had shown, even before this formula was developed, that if you have a horizon, the area of the horizon always increases. That this just comes from solving Einstein's equations, those equations that we discussed before, that have nothing to do with thermodynamics. So it's an interesting consistency picture. OK. So black holes emit radiation. They lose mass. We call that evaporation. Now, this, as I said, was irrelevant for an astrophysical black hole. But let's imagine someone let's say someone came and had some way of making a very small black hole, let's say a 1 kilogram black hole. And so someone gives you this 1 kilogram black hole, and you would say, well, 1 kilogram black hole cannot attract me very much. It's probably not a big problem. Okay? However, due to this effect, the 1 kilogram black hole, using the formula E equal to mc squared, will evaporate and will emit an energy which is equal to its mass. And that energy, if you work out what it is just like a 20 megaton nuclear bomb. So don't accept the 1 kilogram black hole from anyone. Fortunately, there are no such black holes around. And we have described some results for black holes from this approximate method. Remember, all these results are derived by this approximate quantization method for gravity. But there are some questions about black holes which we cannot answer using this approximate method. So for example, what precisely comes out of a black hole? So if you throw in some matter into a black hole, you can throw water, or you can throw, I don't know, gold, and what comes out seems to be just radiation. Can we recover the information of the matter that formed the black hole? And in other words, is this process of black hole formation and evaporation consistent with the laws of quantum mechanics, which says that this information cannot be destroyed? Now, to answer this type of questions, we need the full theory. So now we'll return to the discussion of the full theory. And we really don't have a full theory, but we have a theory under construction, which we call string theory. And now we are having this conference on string theory. And the goal of this conference is to make progress in the construction of this theory, understanding this theory better and extending its range of validity of the things that we understand now to understand more things about this theory. Maybe one way to say this is that our picture of the theory is something like this picture. Okay? So you can see there is a building there, and you're pretty sure there is a building, but we don't have the sharp outlines. We don't know everything about the theory. We have some idea about the theory. Now, my attempt today will be to try to give you an idea without formulas, without mathematics. It will be more impressionistic. Hopefully, you will get the idea that there is some picture, but that will remain to be seen. So what we're going to try to see now is that, well, I'm not going to describe this theory in detail. I'm going to discuss one aspect, which is that we're learning some interesting things about the quantum aspects of black holes. And so we'll focus on one particular aspect. And the aspect that we will focus on is the idea of space-time as an emergent concept. Now, we can motivate this as the following, let's say, question. These are the type of questions you have in the university entrance exams in the US. I don't know if you have those in Canada. But so these are questions about analogies. So water is to atoms as space-time is to. So so we use atoms to describe water. What are the things we use to describe space-time? So space-time atoms, you would say. Are there something like this? And the idea is similar. So we'll talk about an idea that is somewhat similar. But these elementary atoms, or sometimes we call them qubits. So qubits is the basic amount of quantum information, or the basic degree of freedom in quantum mechanics. These atoms are not local in our space, but they are really sitting far away. Okay? And so this is the idea of holography. And the idea is that, so we understand this in some special cases. So some universes with a constant negative curvature. And in these universes, they have, in some sense, some boundary, some region very far away. And in these universes, we can describe everything that is happening in the interior in terms of some qubits, some quantum degrees of freedom that live on the boundary. And these degrees of freedom are interacting a lot with each other, but they don't have any gravity. So gravity only exists in the interior. This is a kind of little picture for this. So the idea is that we have two separate descriptions, two different descriptions. One is we could have a particle moving in the interior. So in these spacetimes, there is a kind of gravitational potential well that keeps particles moving in the interior. Then you have other particles that this funny motion that is represented here tries to give you the idea that these particles are strongly interacting with each other. Now you can ask, well, how you would describe a black hole in this way? So in these spacetimes, you could imagine that you have a black hole in the interior. And the idea is the black hole would correspond to a large number of particles that are strongly interacting and live at the boundary. Okay? And the temperature and entropy of the black hole would come from the temperature and entropy of these particles that live at the boundary. So the idea of this description is that the theory on the boundary obeys the rules of quantum mechanics, and so therefore, so does the black hole in the interior. And then the black holes are consistent with quantum mechanics. But for that, you need to accept this holographic conjecture that space-time and the boundary theory are related in this way. So we'll come to the discussion of emergent geometry. So in this description, geometry is emergent in the following sense. So we have some space-time, and the qubits live far away at the boundary. But the gravitational space-time has one more dimension. So let me try to explain how that happens using an analogy. So imagine a sentence. So we come back to this idea of a sentence. And the sentence says, if a man does not keep pace with his companions, perhaps it is because he hears a different drummer. Now, when you heard this sentence, you probably in your mind divided it into various words, and then you probably grouped the words in some way, analyzing the grammar of the sentence and so on, and the meaning of the sentence. You found the various sub-sentences or sub-clauses and so on, and until you got the full sentence. So in fact, there were also long-distance correlations, for example, between the word man, his, and he, or between the concept of keeping pace and drummer. Okay, that's a kind of deeper level correlation. As we include more words in our analysis, we get to a deeper meaning of the sentence. Okay? So we have, in some sense, an extra dimension, which is the depth of meaning or the direction of meaning in the sentence, of how deeply encoded is a particular concept within this sentence. So in this analogy, the idea is that the state of the quantum system is analogous to a very long sentence that lives at the boundary. And the bulk geometry is doing some analysis of the meaning of this particular sentence. So that's in the analogies, reflecting the correlations that you have between the various words of the sentence, and there are correlations that are encoded that involve short distances along the sentence, and some involve words that are very far away in the sentence. And for example, particles in the space-time could be particular words that are either repeated or have some correlated meaning in the sentence. And a bulk observer, so someone who lives in this bulk, is a bit like a character in a novel whose text is living at the boundary. Okay? So someone who lives in this space-time, that's what it would be. He's also some kind of emergent concept or emergent object in this description. And it's interacting with other emergent concepts and so on. So perhaps a slightly more accurate way to describe this is that the boundary is a superposition of many possible sentences. That has to do with the quantum mechanical aspect that involves probabilities. And the bulk space-time represents those statistical correlations. Now, you can ask, what is a black hole in the space-time? So let's make an analogy for that. So we go back to the sentence. And now we change some words. So here we change the word his to its, and he to she, and so on, and we change these words. And once we change this word, we lose the full meaning of the sentence, of the original sentence. We keep somehow a little bit some of the meaning, but not we lose the meaning at a certain depth. So beyond that depth, we have a kind of horizon. We don't know what this speaker is talking about. Okay? And then if we continue changing words, then this horizon of meaning gets closer to the individual words, and the sentence makes less sense. Okay? And that growth of ignorance has to do with it's represented in the bulk as the area growth. Okay? And we could imagine the situation where we completely change all the letters in the sentence. Now the black hole grows as much as it can grow, and we just don't know we don't know anything. There is no information in this sentence, apparently. And now imagine that the changes in the sentence came from a reversible process. So for example, an encryption algorithm. So in that case, it is possible to reverse the process and recover the original sentence. So that the laws of physics at the boundary change the state at the boundary, similar to changing the sentence, and it's analogous to an encryption process in the sense that it is reversible. And so we can, in principle, undo the formation of the black hole and recover the information. So that's what it would mean to recover the information. Okay, now let me go back and discuss again this idea of portions of a sentence. So if I show you again this sentence, Mary, little lamb, you might have different guesses for what the block word might mean. So there is one that probably you first thought about, but there could be many other ones. So Mary sold the little lamb, Mary killed the little lamb. Okay, that would be a cruel Mary, but maybe she was hungry, I don't know. So you're missing part of the meaning. And so in the same way, we can consider this very long sentence that lives at the boundary, or this very long, very complex quantum state that lives at the boundary, and block off a portion. So you decide not to look at that portion. And when you do not look at that portion, you have some ignorance, and there is an interesting formula characterizing the ignorance that you have, in this case of the quantum systems that give rise to geometry. And this formula says that the ignorance that you have is proportional to the area of a minimal area surface. So you consider a surface that ends at the tips of the region you blocked, and you can let it move, so it can be anywhere, but you find the surface that has the maximal area. And we're in a curved geometry, so if we were in a flat geometry, the surface with the minimal area, would be a straight line. But in the curved geometry, in this particular curved geometry, the minimal area is this surface, so that's the one that has least number of angels and demons, and you can calculate this minimal area. And you divide by L Planck, the Planck length in the interior, and that gives you the entropy. So it's very similar to the formula for black hole entropy, except that we're not talking about the horizon, we're talking about this minimal area. And this is a very important was a very important formula because it related a geometric concept like area to a quantum information concept as this entropy, or amount of information of a blocked region. Now, we can also ask whether we can recover a portion of the bulk if we miss, what we can recover about the bulk if we miss a portion of the boundary. And then the idea is that if you're missing this portion of the boundary, you will miss also this portion of the bulk spacetime. In other words, when you have a very long sentence and you're missing this region, you could imagine that you can recover meaning, or the meaning of the sentence, or let's say it's a novel that is in the regions very far away from, let's say, the pages you lost, but there will be some part that you would certainly not know. And depending on the structure of the novel, you might or might not figure out what's going on, but you certainly will miss something. And so the part of the meaning of the novel that you missed would be this region inside. So that's the analogy. So this idea that the bulk is encoded in the boundary is encoded in a boundary in a way that also similar to how quantum information can be stored in a quantum computer. So in order to remove errors in quantum computers, you store information also in some kind of distributed way, where information is encoded in correlations between different degrees of freedom. And that's called a quantum error correcting code that was developed in the 90s by Peter Shor. and is how quantum computers are supposed to work. And Almeridon and Harlow found more recently that actually we should think about the emergence of space-time using this type of ideas. So all these developments have shown that space-time emerges in some way from quantum entanglement, or in other words, that space-time emerges from correlations in this quantum system. Or another way of saying it, this is that geometry is related to patterns of entanglements or correlations. So it's somehow similar to how meaning emerges from the correlations between words when we have sentences. In fact, people use ways to describe, so I'm not going to explain this picture, but this picture appears in papers of tensor networks. And so this is some way to encode quantum correlations in a system. And Guilford Vidal was one of the developers of these ideas. He was here at the Perimeter Institute, and I think he recently left and worked in artificial intelligence. So he went from the quantum world to the world of sentences. But what you can see is that the pictures are kind of a similar structure. So this analogy is actually conceptually, well, it's kind of vague, but it has some sense. Now, let me make a comment. So this idea that the space-time can be emergent from quantum degrees of freedom implies in principle that you could make a little quantum, if you have a quantum system and you can manipulate it as much as you wish, then you could make a little tiny small universe that is governed by Einstein's equations. So just to make the tiniest universe we can imagine that is governed by Einstein's equations, we would need about 10,000 qubits. Okay? So quantum computers today have about 50, 100. So there is some way to go. But, well, maybe we'll get there sometime. In contrast, our big universe, the universe we live in, we think we would need of order 10 to the 120 qubits. And in addition, our universe is expanding, and we don't really know how to describe it using these methods. So now I'm going to discuss an interesting case of the relationship between entanglement and geometry. It's a little more dramatic case of how geometry can emerge from entanglement. And this is just going back to a funny feature of the simplest black hole solution. And it is the fact that the simplest solution of vacuum Einstein equations describes actually two black holes. So these are two black holes that are very far away, but they are sharing a single interior. So in some sense, there is a geometry which at some moment in time looks a bit like this. So they are far away, so this is the far away distance, but they are really connected through the interior. Now, the interior is time dependent, so the distance between the two through the interior changes. And let's say at time equal to 0 is like this, and then as time progresses, it becomes thinner and more distant in such a way that if you were a traveler trying to go from one side to the other, you wouldn't be able to go. You will fall into the black hole. You will get crashed at the black hole singularity, and you will not be able to traverse this wormhole. But the space-time that it describes has these connections. And the interpretation is that this geometry corresponds to two entangled black holes. So each black hole has some entropy, some degrees of freedom, some qubits. That if you look at one of them, they are thermal, they have some randomness. But if you look at two of them together, that randomness is correlated in such a way as to make a pure coherent whole. And that pure coherent whole gives rise to a geometry which is connected through the interior. So let me give you another analogy for this connection through the interior. So let's imagine we have two sentences. So we have the same sentence we had before, and now we have the same sentence here in the bottom. It's the same sentence, but in Spanish. Okay? And so if you analyze these sentences, the words are quite different. So the grouping of letters is different. But if you start analyzing it, you get to a point where the two sentences have the same common meaning. So you would have this region of the geometry is doing the analysis of the English sentence, and this region of the geometry is giving the analysis of the Spanish sentence. And at some point, you get to the meaning of the sentence, which is common to both cases. So this is a bit like analogous to that wormhole. So they have this common meaning. Now, there's a small variation of this process where you bring the two black holes closer together, and you allow some simple form of interaction between them. And in that case, then the wormhole can become traversable. In that case, you can indeed travel between one side. So first of all, the black hole ceases to be a black hole. There is no horizon anymore. And then you can go through this wormhole. I won't explain all the details. But in quantum mechanics, this process of allowing some interaction and then you going through the wormhole is related to quantum teleportation. So let me, what time am I supposed to end? Okay, well, a few more minutes. So some analogy for this business of quantum teleportation through a wormhole. So this process has three elements: entanglement, communication, and this idea of wormhole. So let me just make a little bit some classical analogy. So imagine that Bob and Alice had been married for many years. So they share many common memories. Okay? So that means that Alice can send Bob, let's say, a look or just simply a few words, and Bob will know what she means. Okay? So in some sense, there was an idea, which is a much more complex thing. Well, an idea that got transferred from Alice's mind. This is kind of representation of her mind with all the meaning and so on inside, and Bob's mind. So the idea went from Alice to Bob, and it managed to go thanks to the fact that they shared all these common memories and just some simple look. So if a person from the outside that only hears the word or saw the look would not be able to guess what the idea was because they don't have their common experience. Now, I'm not talking about this, but there was a recent mini revolution in our field about similar wormholes that were important for understanding how information is encoded in Hawking radiation and the black hole interior. So I won't discuss that. So in conclusions, I emphasize the fact that quantum systems can give rise to a geometry, this emergent geometry, and that the geometry of our own space-time could be emergent in a similar way. We really understand this for universes that are a bit different from ours, that have, let's say, mostly negative curvature. Our universe is a bit different because it has positive curvature. Now, an interesting consequence is that we could make these little tiny universes in the laboratory, very, very tiny. And in the future, we hope that this will lead to an understanding of the singularity inside of black holes. We don't have that yet. And after understanding that singularity inside the black holes, which has to do with the Big Crunch, hopefully we'll then understand the singularity at the beginning of the universe, which is really the biggest question in our field and the thing that really drives us forward to keep investigating this theory further to understand how the universe really began. And with that begin, we just end. Thank you.
Thank you so much, Professor Maldacena, for your fascinating talk. We will now open the floor to questions. So for those here in person, there's a microphone set up in the stairs to the audience's right. We'll ask that you limit yourself to just one question relevant to the talk, just to ensure that everyone has a chance to ask their question. So please form a line here. We have someone already. Please go ahead.
Thank you, Professor, for your whirlwind tour of the recent developments in quantum mechanics. I have one 10-part question. No, but so as a string theorist, you're obviously partial to unification of quantum mechanics and general relativity. Unification based on string theory. But what are other leading candidates for unification of these two understandings that are not based on string theory?
Yes. Well, I mean, the question is the idea that quantum mechanics and quantum mechanics and general relativity should be put together is very old. People had various approaches. String theory, I think, is the one that is further along. But there are ideas, for example, triangulating your space-time and then integrating over all, or summing over all possible ways of doing that, defining a quantum theory in that way. There is something called loop quantum gravity. There are various other ideas that capture some aspects of this story. But I would say that if you want to get to the point where you really derive Einstein's equations and a continuum geometry, just to string theory is the only one that can do that. Yeah.
Hi, thank you for the talk, Professor. So my question is, in approximate theory, you mentioned that entropy is proportional to the area. But if entropy is increasing, shouldn't the size of black hole should keep on increasing and not evaporate?
Very good question. Yeah, very good question. So the entropy is equal to the area in the classical theory. So actually, when you do this approximate approach, the entropy gets an additional term, which is the entropy of the quantum fields that live outside the geometry. And so the full entropy of the system outside is the area plus the entropy of the fields outside. Now, when the black hole evaporates, the black hole becomes smaller, the area becomes smaller, but there is Hawking radiation. And because Hawking radiation is thermal, the entropy outside has also increased. And in fact, it increases more than the decrease of the area, so that the total entropy actually increases. This is something that was proven by Aaron Wall in about a decade ago. So it's relatively recent. Yeah, sure.
No one knows how to make a black hole, it was said in the meeting here, 2020, February. But 20 years before, in Scientific American, it more or less had the same argument. You described traversable wormholes, and the warp drive is sort of a transformation of that. In Illusion of Gravity, which you didn't mention, they just turned on the RHIC, and you said at the end, it was too soon to tell, but it may be generating tiny black holes from the ADS correspondence. Do you still think that in the more recent Scientific American, they described sort of the low viscosity, but they attributed it to the strong force? But the strong force is made of gluons, and you also mentioned gluons. Do you think you could, in the fifth dimension, as you described, generate some sort of chain reaction to create this bubble? What are your thoughts?
Okay, well, your question contained various different elements. Let me see if I can say. Well, first of all, before the LHC turned on, people discussed that perhaps it could make black holes. The LHC has turned on and has not produced any black holes, as far as we have seen. That was possible in some scenarios. So that's one point, at least not four-dimensional black holes. You can, I wasn't, yeah, other parts of your question refer to the type of quantum system that has known gravity descriptions. And there is one example of a quantum system that involves particles similar to gluons, so similar to the particles that govern strong interactions in nature. It's a theory which is, let's say, a cousin of the theory that describes strong interactions, so it has gluons and also some other particles that we don't have in nature. But when you put all those particles together, they give rise to this 5 extra dimensional space-time. And in that description, when you have a collision of these particles, you can make a black hole in the 5th dimension, so in the extra dimensional space. From the point of view of the boundary theory, that black hole is viewed as a gas of particles similar to what we had in one of the transparencies, where we had the particles moving at the boundary. So it's described as a ball of gluons, or a quark-gluon plasma, it's called. And so this correspondence, this relationship, can then be used to calculate, or as a toy model for trying to understand that those processes in QCD. So I'm not saying QCD is the theory of strong interactions. So for the theory of strong interactions in nature, we don't know what this 5-dimensional description would be. But for similar theories, we do know. And for those, they can be used as a toy model. Thank you.
tilt the microphone down. Yeah, perfect.
Would we be able to harness Hawking radiation or any other energy from a black hole?
Yeah, that's a good question. So if we look at the black holes that we have in nature that are known to exist, no, because they are, first of all, they are very far away, and they emit very little Hawking radiation. There is more matter falling into the black hole than there is radiation coming out for those black holes that exist in nature. Now, if you ask me what's theoretically possible, right? The best possibility is to have magnetically charged black holes. So if you had, I told you that black holes that have 1 kilogram would explode like a nuclear bomb. Now, if you had a magnetically charged black hole, so that's very difficult to make. We think they can exist theoretically, but they would be super difficult to make. But if you could make them, well, if they existed for some reason, then those would emit Hawking radiation and would settle into a kind of black hole at 0 temperature that's not emitting Hawking radiation. Then you can take some matter and drop it into this black hole, and that matter that you are dropping in would almost instantly be converted in Hawking radiation and would be a source of energy. So that's one scenario you could have. It's very science fiction-like, very unlikely to be realized for many reasons. In particular because we don't think nature naturally produces these magnetically charged black holes, and making them artificially seems exceedingly difficult.
You talk on the view that time here had a beginning, so I was wondering what your thoughts are on these theories if time didn't have a beginning, like if always
Yes. We draw this picture with something that somehow starts here, and what you're asking is, could there be something before this point, some other universe? Time existed before the Big Bang, and then something happens here, and well, we don't know. Maybe we could have it, maybe we cannot have it. But the point is that we don't understand, until we understand what happens here, we cannot really know for sure. So people sometimes say, oh, perhaps there existed. I mean, there are some people who speculate and say, well, maybe there was a time before the Big Bang, and then they make some theory of what will happen. But that's not really a well-defined theory. It's one of these theories where you say, well, something existed before, then a miracle happens here, and then, we don't have a well-defined theory that allows us to go from before to after. And part of the question of understanding what happens here is to be able to answer that, your question, which is a very good question.
Thank you so much, Professor Maldacena. That's all the time that we have tonight for Q&A. So I want to thank everyone for joining us, both here at Perimeter and online. And let's all thank Professor Maldacena again for his wonderful lecture.